DC biasing of bipolar junction transistors part 2. In this video clip we're going to look at a couple of examples to show you how we can calculate things when we're using fixed bias circuits. So example 1 is here is a fixed bias arrangement, and we have to find the following: A, the collector emitter voltage; B, the collector current; C, the base resistor RB; and D, the collector resistor RC. So we'll begin by first of all reminding ourselves that the voltage between the collector and the emitter is 6 volts. So we can immediately write, because the transistor is grounded, this is at 0 volts. So the collector voltage is 6 volts. So the difference between the two, collector emitter voltage, is in fact just 6 volts. So the first part is straightforward. Now the collector current is the next thing. So we're going to remind ourselves that the beta value, 80, is the ratio of the collector current to the base current. Now in this example we're given the base current is 40 microamps. So it's only a matter of substituting into that equation. 80 times 40 microamps gives us 3.2 milliamps for the collector current. Okay, so first two parts very straightforward. Now we move on to calculating the base resistor, and to do that we are going to do what we mentioned in the first part 1, where we imagine that the collector side of the circuit is disappears, and we just focus on the base side of the circuit and apply Kirchhoff's law, which is that the sum of the voltages round the circuit, so the base current times the base resistor RB, that voltage that's developed across the base resistor, plus the voltage that's between the base and the emitter, which is VBE, the sum of those two must be equal to the power supply, which is 12 volts. Okay, so now VBE, as we mentioned, is 0.6 volts. So we've got, and the base current we're given is 40 microamps. So plugging that into this equation, we get 40 times 10 to the minus 6 amps times RB plus 0.6, which is the voltage across the base emitter when the transistor is conducting, and that's equal to 12 volts. So rearranging this and dividing through, and we end up with 285 k ohms for the base resistor. So that's straightforward. So these are our values so far. We've got the base resistor, which is we've calculated at 285 k, collector current 3.2 milliamps, and VCE 6 volts. So all we're left to do now is to calculate the collector resistor. So to do that, we're going to ignore the base side of the circuit and focus on the collector side, and once again apply Kirchhoff's law, which is that the 12 volts has got to equal the sum of the voltage dropped across the resistor RC, which is IC times RC, plus the voltage that's between the collector and the emitter, which is VCE, and in this case it's 6 volts. So we can write down IC RC plus VC must be equal to 12. That's 3.2 times 10 to the minus 3 times RC plus 6 equals 12. And taking the 6 over and dividing both sides by 3.2 times 10 to the minus 3, we end up with 1.9 K. So there are our values for our resistors, and so we can move on to the next example. In this example, we now have a series of things we want to calculate. The first thing to note is that sometimes on some authors like to put Q next to the base current and Q next to the collector current to remind you that this is the quiescent currents. So instead of IB that we had in example 1, we now have IBQ, but it's exactly the same current. Okay, so we'll start off with the first part, which is to calculate IBQ. To do that, we're going to do Kirchhoff's law again, which is that the voltage dropped across the base resistor plus the voltage between the base and the emitter has got to be equal to 16 volts. The voltage dropped across the base resistor is IBQ times RB, and the voltage between the base and the emitter is VBE. Okay, so let's plug in our values. We know that VBE must be 0.6 for the transistor to conduct, so we can plug that in straight away. And also, you'll see that I've marked that as the answer to part E on this question. Then we're going to use the Kirchhoff's law formula. IBRB plus VBE is 16 volts, the supply voltage. Plug in 510k for RB and 0.6 for VBE. Rearrange and calculate our value for IBQ, which turns out to be 30 microamps. Okay, so that's part A completed. Now we're going to move on to now we want to know what IC is, the collector current, and you'll see I've accidentally dropped the Q following the IC on this diagram, but don't worry about that. It's exactly the same current, and we just need to remind ourselves that beta is the ratio of the collector current ICQ I should say, to the base current IBQ. So we've got the base current, so we can rearrange this to get the collector current, which is 120 times 10 to the minus, 120 microamps. 120 for beta times 30 microamps. 3,600 microamps, which I've changed to milliamps, 3.6 milliamps. So the collector current is 3.6 milliamps. So that completes the part B. You notice with some of these questions, you don't have to answer them in the order in which they're listed. So you can go straight to any part of the question. As long as you get them all done, it doesn't really matter. So now I'm going to focus on the collector side of the circuit to work out what VCEQ is. Again, applying the Kirchhoff's principle, IC times RC, the voltage dropped across the collector resistor, plus the voltage dropped between the collector and the emitter, has got to equal the supply voltage. So ICRC plus VCEQ is 16 in this case. Okay, now we know IC and RC, so we can plug those straight in, no problem. And the only thing we don't know is VCEQ, so we just leave that as it is, and that's equal to 16. When you rearrange this, we end up with 6.5 plus VCEQ is 16, and therefore VCEQ is 9.5 volts. Always make sure, of course, that this has always got to be less than the supply voltage. Okay, so 9.5 volts is less than 16, so that's okay. So now we're left with the last two parts, D and F, to solve. Well, these are actually quite trivial, because if you think about it, VCEQ is 9.5 volts. We know that the transistor is grounded. There's no emitter connected, resistor connected in the emitter. Although later on we'll find in biasing circuits that we're going to look at later, there are going to be resistors in the emitter for stability reasons. But at the moment, this emitter is grounded, so VE is in fact 0. And therefore, if there's 9.5 volt potential difference between the emitter and the collector, then the collector must be at 9.5 volts. So VE is 0 and VC is just 9.5. Rather trivial, actually. In fact, we could have plugged that straight in at the beginning, almost at the beginning. Okay, so that completes example number 2. And later on, we're going to look at some other biasing methods in part 3, and we'll do some similar calculations on that as well. Okay, so I hope you enjoyed this video clip.